All right, so it is time to talk about lightweight stream ciphers. So we will start with basic definitions, then I will give some lightweight examples. So in order to understand stream ciphers, we have to understand one-time pad, which is also known as the unbreakable cipher. So this is a question everybody asks when they first hear cryptography, because people want to know if they can design something that is unbreakable. So the answer is yes, and this is how it works. So you want to encrypt a long sequence of long text, let's say. So what you do is you initially generate a very long sequence of random bits. So this should be as long as the text you are going to encrypt. So of course, I'm saying bits. You can also modify it to characters, but it is easier to understand with bits. So you write it on a single page with a very small letter. So this is why we call it one-time pad, because you write it on a notepad. We call it one time because you are going to use it only once, okay? So you randomly generate zeros and ones, a very long sequence, and give it to the person you want to communicate. So you can only send a single text with this secret key, okay? So what you do is as follows. You convert your plain text into zeros and ones, then XOR your plain text with this one-time pad and obtain ciphertext. The person who receives ciphertext XORs it with the one-time pad and obtains the plain text. So as simple as that. So if you are not familiar with the XOR operation, it means exclusive OR, and it works like this. So assume that this is your plain text. You wrote it into as zeros and ones, and your one-time pad is this, which you randomly generated. And I have to insist that you have to generate it randomly. Okay. XOR operation works as follows. It is like a normal addition. For instance, when you add 1 to 0, you obtain 1. You add 0 to 1, you obtain 1. But once you XOR 1 and 1, you obtain 0. So this is also what happens when you do addition modulo 2. But something is different. Now you don't have a carry bit. If it were an addition modulo 2, then you would have a carry bit here. So it would become 1. But in the XOR operation, 1 XOR 1 is 0. So in such an XOR operation, if we think these as columns, values only affect the column they are interacted with. So bits only affect bits. So it is one of the easiest operations that you can do, and it is really fast on software and hardware. But the thing is that one-time pad must be truly random, and it can only be used once. This is very, very important. So one-time pad provides perfect secrecy because ciphertext provides no information about the plain text. This comes from this XOR operation because you selected this randomly. After this XOR operation, if you can guess from the ciphertext what the plain text bit is, then this means that you can also guess this one-time pad, but it was generated randomly. So this is why we call it perfect secrecy. So there's some kind of a formal proof at the end. Instead of working with bits, one can work on letters or characters, depends on how you define the alphabet. Usually printed on a single page with very small letters, hence the name one-time pad. Problems are as follows. The main problem is key is too long. Because if you want to encrypt, for instance, 1 megabyte, then you have to generate 1 megabyte of random bits and give it to the person beforehand. So this is very important. And the problem, and also we are forcing you to use a key only once. This means that if you want to send, for instance, 10 WhatsApp messages, you have to generate 10 keys like this, give it to the person beforehand, and then use it through WhatsApp. So this is why WhatsApp is not using this, okay? So this also causes the problem of key distribution. You have to give all your initial secret keys beforehand in a secure way through a secure communication channel. And also the third problem is randomness. Some people are having a hard time for randomly generating bits, and this is a very important issue. Most of the time, people attack crypto systems through randomness. For instance, we always say that you choose a secret key, and we are saying that you should generate in a random way. So if your random number generator is not good, then we can guess what your secret key is. So as you can see, there are 3 problems, and all of these problems are very important problems. But of course, randomness can be solved. You can have a very nice random number generator or a random bit generator. But key distribution here is a problem, and having very long keys is also a problem. You have to generate beforehand. So I don't know if I say it in the following slide, but we know that Washington and Moscow exchanged many this kind of one-time pads, maybe 20 or 30 years ago, so that in the future, if something bad happens and if all of your algorithms are broken, they can communicate for a short time using those one-time pads. Okay, so they're still used in real life. So I said that you can only use a secret key only once. One-time pad has to be used only once. So why this is a problem? Consider the following scenario. Assume that the adversary captures 2 ciphertexts, C1 and C2, which were generated with the same key. So this means that C1 actually equals to P1 XOR K, secret key, one-time pad. But C2 is also equals to P2, second plaintext, XOR with the same secret key, one-time pad. So the adversary only captures C1 and C2, and they don't mean anything to them. But if you XOR C1 and C2, the attacker XORs these 2 values. But in the background, this actually means the following XOR operation, right? Because C1 is this and C2 is this. But since this addition modulo 2, K XOR K actually cancels each other. So you end up with P1 XOR P2. So you don't know what is P1 or P2, but you know their XOR value. So this is a huge problem because the plaintext has a redundancy. And from this part, you can capture some or the whole of P1 and P2. And this actually happened during the Second World War. I think it was called Venona project. Americans listened many Russian communication because they assumed that they were using the same one-time pad, and they actually did that. So they could easily capture a lot of plaintext. Okay. So why are we talking about one-time pad? As you can see, this is hard to use. There are many problems, but this idea actually leads us to stream ciphers. So stream ciphers try to achieve the one-time pad-like security by generating pseudo-random key stream from a short key. So instead of choosing a very large one-time pad, we actually choose a short key, like 128 bits, but design an algorithm so that that short key actually produces zeros and ones, which look random. And we will use it as a key stream, which actually works like this. So it will work like a one-time pad. This is the whole idea. But of course, now, since we moved from random to pseudo-random, the security will not be as good as the one-time pad. Okay, and we are saying it is pseudo-random because from a short key, you cannot generate a longer random value because it is against information theory. Okay. So recall that we categorize symmetric key encryption algorithms as block ciphers and stream ciphers. So there is a misunderstanding in the definitions, because since the name is block cipher, people know this. Block ciphers operate on large blocks of plaintext data with a fixed transformation. Like this block size can be 64 bits, 128 bits, and so on. But since they work on blocks, people define stream ciphers as follows. Stream ciphers work on bits. This is a very wrong definition. Okay, the difference between stream cipher and a block cipher is not that stream ciphers work on bits. Actually, there are many stream ciphers that work on blocks. Okay, the definition, the difference does not come from the way they handle it. Actually, the difference is that block ciphers have a fixed transformation working on blocks, but stream ciphers operate on individual plaintext digits. This can be as large as, again, 64 bits, with a time-varying transformation. Actually, stream ciphers has an internal state. This is why the output changes depending on time. Okay, so this is the main difference. So let's recall, a block cipher processes the plaintext in relatively large blocks at a time, and the encryption function is same for every block. right? A block cipher can be considered as a bijective function which takes two inputs, plaintext and the secret key, and this function provides the ciphertext. Some mode of operations can turn a block cipher into a stream cipher. We actually already seen them, like counter mode. But at that time, we didn't know what a stream cipher is. Now we are going to understand what the stream cipher is, and then we will understand why we call that those mode of operations turn the block cipher into a stream cipher. So a stream cipher processes the plaintext in small blocks, sometimes as small as a single bit, sometimes as large as 128 bits. There are many variants. Contrary to a block cipher, a stream cipher has a sort of memory, which we call the state rho t at the time t, as it processes the plaintext. Okay, this state is an input of the encryption algorithm. We can consider a stream cipher as a pair of functions f and h as follows. F is the next state function. So you have a state. Depending on that plaintext value and the secret key, you obtain the next state. But there is also an output function which provides output depending on the current internal state, the plaintext, and the secret key. Okay. So in order to visualize what a stream cipher is, let me first give you a smaller component of it, which is called LFSR. Okay. These are very famous in stream cipher designs. LFSR is short for linear feedback shift registers. Okay, here our aim is to generate a long sequence from a shorter value. Okay, so here these blocks actually store bits, and here you provide the output. So once you, for instance, at a single clock, once you run this LFSR, you take these values and XOR them. So sometimes there are no lines here, sometimes there are. So the CIs determine that. So you XOR all of them, and the output will be added to this feedback. But since the place is filled, you actually shift everything one bit to the right. So this bit is produced as output. So everything is shifted one bit. So there's an empty place here. So you write this value here. Okay. So from an internal state, you provide actually an output. Okay. From a short state, for short register, you can produce an output which doesn't repeat itself for a very long time. In order to give a better example, if this is L bits, if you choose these lines in a good way, then you can produce 2 to the L minus 1 output bits until you start repeating yourself. That is actually called your period. Okay. So I explained on the picture, but let's read the definition from the slides. LFSRs are very common in stream cipher designs. At one tick or a clock, the register produces one bit output here. State is shifted one bit, and the new bit is obtained by the XOR of the bits of the previous state that has a tap point. So we call these tap points. So you don't have to have all of these tap points. Sometimes, for instance, you can design an LFSR which has only 2 tap points like this. So these are zeros. So you only XOR these 2 values and write it here. So choosing those tap points actually affects your quality of your LFSR. But there's a very nice mathematics behind it. Actually, you choose a minimal polynomial, which actually determines which places you are going to put a tap point. Okay. If you don't choose these tap points according to a minimal polynomial, then the output will have shorter periods. This is why I'm saying that there's a nice mathematics behind it. So yes, an n-bit LFSR can have at most 2 to the n minus 1 different states. So by states, I mean the values that fill this place. You might ask why there's a -1 here, because if you fill with all zeros, then, XORing these values wouldn't provide anything. So, it would produce zeros all the time. So internal state can be anything except all zeros in this example. And the internal state will change and change until you can represent every possible n-bit state, which is 2 to the n -1 because of all zeros. Thus, it repeats itself after 2 to the n minus 1 bits. So it is called period. Maximum period is obtained when the tap points are chosen according to a degree n primitive polynomial. Okay, sorry, I said minimal, but primitive should be the correct value. By minimal, when you have the first constant as 1, you call it a minimal polynomial, but by primitive, we mean something else. Okay. So here's an example, actually, which we will see in detail in a few minutes, but let me show you how can you design a stream cipher, a key stream generator from a few LFSRs. So here are 3 LFSRs. So 19 bits, 22 bits, and 23 bits. If you sum all of them, actually, they end up with 64 bits. This is a 64-bit a stream cipher that uses 64-bit key, which is called A51. This is a GSM standard. It's 2G. So it works like this. At a single tick, when you want to provide an output, you actually take this value, take this value, take this value, and XOR it and provide the output. And since you are going to shift everything 1 bit, you have to feed the new value from here. Okay, so that value actually depends only on this 4 bits. So in this LFSR, the tap points are here, 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 and here. In this one, you only have 2 tap points. Here you have 4 tap points. So having less tap points actually provides you speed, right? Because this means that you are going to do less operations. Since this is a very old standard that were used in early mobile phones, actually today we are still using it in some cases, but still. As you can see, this is a very simple design. So when you start talking, actually your voice turns into a plain text, and it is XORed with this output and provided as a ciphertext. So the person who is going to decrypt your voice should also have the same internal state so that they can provide the same output, so that they can XOR it with your ciphertext and obtain your voice as a plain text. This is the whole idea behind the key stream generator stream ciphers. Okay, I hope this is clear. But the algorithm, of course, works in a more complicated way, and we will see it in a detail. But let's focus on now the key stream generator. So it may be the case that the next state function does not depend on the plain text, as in this picture, because here we don't even have the plain text at all. So this is your, for instance, current state. Once you run it 1 tick, you update it, so your next state is modified depending on these values, but it doesn't depend on the plain text. So in those cases, we call it a key stream generator. So in such a case, key stream is produced by an output function G. So in this example, our output function G is just the XOR of these values. So your G function actually is this, right? So you provide output, which we call a key stream. So this is the part which we call that it looks pseudo-random. Okay. Then the encryption function combines the key stream with the plain text. So next state function is just current state with the secret key, provides the next state. Output function looks at the current state and the key and provides some output. And the encryption function takes this output and combines it with your plain text and provides ciphertext. This is how a stream cipher works. So this type of stream ciphers are known as key stream generator ciphers. They have the advantage that the key stream can be pre-computed without using plain text or ciphertext. An important example is the binary additive stream ciphers, where H is the bit-by-bit addition of the key stream and the plain text, which I actually defined A51 algorithm like this. Block cipher mode of operations like counter mode actually converts the block cipher into a binary additive stream cipher. As you can see in the counter mode, you are actually encrypting counters and obtain some outputs. So this is why I call them a key stream. Then you XOR it with your plain text and obtain the ciphertext, right? So some block ciphers can be used as a stream cipher due to the mode of operation you choose. But of course, they are still block ciphers, but you use them as a stream cipher.